We consider a problem of hierarchical forecasting. In particular, we provide a novel forecasting method for hierarchical structures without critical assumptions required for existing methods, even in the presence of high-dimensional hierarchies. Hierarchical structure can be found in many places. Forecasting a structure with multiple levels is a central problem for many organizations. For example, consider a multinational company. Its global sales is at the highest level, which is the sum of the country level sales. Then next, city level sales, sum of which is equal to the country level sales. Further down, possibly county or borough level sales in the middle, and finally store level sales at the bottom. When it comes down to forecasting sales in this structure, you notice this is by nature a multivariate forecasting problem. Vertically, there exist hierarchical aggregation constraints. Horizontally, we want them to be precise. Independent forecasting order series might be problematic because in doing so, hierarchical aggregation constraint might be ignored. Summing the individual bottom level forecast is also problematic because it might cause forecasting upper levels in the hierarchy might not be precise. These problems get worse in the presence of high-dimensional hierarchies, which is the case in most interesting examples. Our method is an attempt to rectify these issues with less stringent assumptions. Existing hierarchical forecasting requires crucial assumptions. The base forecast should be unbiased, and even the revised forecast need to be unbiased. However, it is usually not the case in practice. Specifically, we employ an idea of the empirical risk minimization. Y sub t plus h denotes the h-step ahead realization of a target variable. S is a matrix representing the hierarchical structure. P matrix is the quantity of interest which ensures minimizing the forecast error as well as the satisfying hierarchical aggregation constraint. Y hat is the base forecast for the h-step target variable. We estimate P matrix, which is the minimizer of this objective function. We also extend the empirical risk minimization by adopting a regularization represented by the highlighted term. This paper investigates an array of statistical and algorithmic features of the proposed estimator with various empirical implementations using simulation and real data studies.